Today we'll be talking about ownership. Ownership is Rust's most unique feature and has deep implication for rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we will talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. What is ownership? Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some language have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the program must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that more experienced you become with the rules of ownership system, the easier you will find it to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you will have a solid foundation for understanding the features that make Rust unique. In this chapter, you will learn ownership by working through some example that focuses on very common data structure, string, the stack, and the heap. Many programming languages don't require you to think about the stack and heap very often, but in a system programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Part of the ownership will be described in relation to the stack and heap later in the chapter. So here is a brief explanation. In preparation, both the stack and heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stored values in the order it gets them and removes the value in the opposite order. This is referred to as last in first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is called popping off the stack. All data stored on the stack must have a known fixed step. Data with unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, mark it as been in use, and returns a pointer which is addressed to of that location. The process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating because the pointer to the heap is a known fixed size. You can store the pointer on the stack, but when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you entered, you state the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold the data, then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack because you have to follow pointer to get there. Contemporary processors are faster if they jump around in less memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A, then an order from table A, B, then from A again, and then from B again would be much a slower process. By the same token, a processor can do its job better if it works on a data that's close to other data as it on a stack rather than finding away as it can be on the heap. When your code calls a function, the value processed into the function, including potentially pointers to data on the heap and the function's local variable, get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what part of our code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often, but knowing that the main purpose of ownership is to manage heap data can explain why it works the way it does. Ownership rules. First, let's take a look at the ownership rule. Keep these rules in mind as we work through the example that illustrate them. Each value in Rust has an owner. There can be only one owner at a time. When the owner goes out of scope, the value will be dropped. Variable scope. Now that we are past basic Rust syntax, we won't include all the fn main code in sample. So if you are following along, make sure to put the following sample inside a main function. As a result, our example will be a bit more concise, letting us focus on the actual details rather than the boilerplate code. As a first example of ownership, we will take a look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following example. Okay, so this is a slice string, right? The variable s refers to a string variable where the value of the s of the string is hard coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Listing for 1 shows a program with comments annotating where the variable s would be valid. S is not valid here, it's not yet declared. S is valid from this point forward. The scope is now over and s is no longer valid. Okay, in other words, there are two important points in time here. When s comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and variable and when variables are valid is similar to that in other programming language. Now we'll build on top of this understanding by introducing the string type. The string type, to illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data type section of chapter 3. The types covered previously are of known size and can be stored on the stack and popped off the stack when their scope is over. Can be quickly and trivially copied to make a new independent instance if another part of the code needs to use the same value in different scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data, and the string type is a great example. We will concentrate on other part of string that relates to ownership. These aspects also apply to other complex data type where whether they are provided by the standard library or created by you. We will discuss string in more depth in chapter 8. We have already seen string literals where a string value is hard coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they are immutable. Another is that every string value can be known when we write our code. For example, if you want to take user input and store for this situation, Rust has a secondary string type called string. Okay, so I think slice string and string literal are the same thing. This type manages data allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. The double colon operator allow us to namespace this particular from function under the string type rather than using some sort of name like string underscore from. We will discuss this syntax more in the method syntax section of chapter 5, and when we talk about namespacing with modules in path for referring to an item in the module tree in chapter 7. This kind of string can be mutated. Okay, so I can write something like this and add some. Okay, so let me try this. So output should be hello world. Okay, so what's the difference here? Why can string be mutated but literals cannot? The difference is in how these types deal with memory and allocation. In case of a string literal, okay, string slice are also called string literal. In case of a string literal, we know the contents at compile time, so the text is hard coded directly into the final executable. That is why string literals are fast and efficient, but these properties only come from string literals immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable growable piece of text, we need to allocate an amount of memory on the heap unknown at compile time to hold the contents. This means uh, the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. That first part is done by us. When we call string colon colon from its implementation request the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In languages with garbage collector, the GC keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a GC, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we will waste memory. If we do it too early, we will have an invalid variable. If we do it twice, that's a bug too. We need a pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned when a variable that owns it goes out of the scope. Here's a version of our scope example from okay. S is valid from this point. Okay, there is a natural point at which we can return the memory we can return the memory our string needs to the allocator when S goes out of scope. When a variable goes out of scope, Rust calls a specific function for us. This function is called drop, and it's where the author of string can put the code to return the memory. Rust call drops automatically at the closing curly bracket. In C++, the pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization, RAII. The drop function in Rust will be familiar to you if you have used RAII patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situation when we want to have multiple variable use the data we have allocated on the heap. Let's explore some of the situation now. Variables and data interacting with move. Multiple variables can interact with same data type in different ways in Rust. Let's look at an example using an integer in listing 4-2. Let x equal to 5, y equal to x. Now I think we don't have to worry about ownership here because they are string. We can probably guess what this is doing, binding the value of 5 to x. Then we make copy of the value in x and bind it to y. We now have two variables x and y both equal. This is indeed what is happening because integer are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Now let's take a look at string version. So let s2 s1 now s2 equal. Now I think you can't use s1 after this because the ownership of s1 ends as soon as it is assigned to s2. So let's check. Okay, now if I do print ln of s1, I think it should give me an error. Okay, borrowed value error. Okay, this looks very familiar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in s1 and bind it to s2, but this isn't quite what happens. Take a look at figure 4-1 to see what is happening to string under the covers. A string is made up of three parts: shown on the left, a pointer to the memory that holds contents of the string, a length and a capacity. This group of data is stored on the stack. On right is the memory on the heap that holds the contents. The length is how much memory in bytes the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. The difference between length and capacity matters, but not in this context. So for now it's fine to ignore the capacity. When we assign s1 to s2, the string data is copied, meaning we copy the pointer, the length and the capacity that are on the stack. We do not copy the data on the heap that pointer refers to. In other words, the data representation in memory looks like figure 4-2. The representation does not look like figure 4-3, which is what memory would look like if rush inserted copy the heap data as well. If rush did this, the operation s2 equal to s1 could be very expensive in terms of runtime performance if the data on heap were large. Earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4-2 shows that data pointers pointing to the same location. This is a problem when s1 and s2 goes out of scope. They both will try to free the same memory. This is known as double free error and is one of the memory safety bugs we mentioned. Memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety after the line let s2 equal to s1, Rust considers s1 as no longer valid. Therefore, Rust doesn't need to fire anything when s1 goes out of scope. Check out what happens when you try to use s1 and s2 is created. It won't work. So we have something like this, and then s2 equal to s1. You will get an error like this. Yeah, we already checked this out, right? If you have heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy. But because Rust also invades the first variable instead of being called a shallow copy, it's known as a move. In this example, we would say that s1 was moved into s2. So what actually happens is shown in figure 4-4. That solves our problem with only h2 valid. When it goes out of scope, it only will free the memory we are done. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Variables and data interacting with clone. If we do not want to deploy the heap data of the string, not just the stack data, we can use a common method called clone. We will discuss method syntax in chapter 5, but because methods are a common feature in many programming language, you have probably seen them before. Here's an example of clone method in action. Let s1 equal to string : from hello, and let s2 equal to s1 dot clone. Println s1 equal to this. Okay, this works just fine and explicitly provides the behavior shown in figure where the heap data does get copied. Okay, let's try this. Okay, no error because the data was cloned, because s1 is cloned. But if you try to use s1 and s2 after this, then I think you will get an error. Again, if you write okay, let's try this. Okay, so I guess using them in multiple statement is not okay. Now you get an error. Error for s1 because it was borrowed. This works just fine and explicitly produces the behavior in figure 4-3 where the heap data does get copied. When you call a when you see a call to clone, you see that some arbitrary code is been executed, and that code may be expensive. It is a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about yet. The code using integers, part of which was shown in listing 4-2, works and is valid. Okay, but this code seems to contradict what we have just done. We don't call have a call to clone, but x is still valid and wasn't moved to y. Yeah, because this is an integer, right? The reason is that the types such as integer that have a known size at compile time are stored entirely on the stack. So copy quick to make that means there's no response we would want there's no reason we would want to prevent x from being valid after we create the variable y. In other words, there is no difference between deep and shallow copying here, so calling clone wouldn't do anything different from the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types that are stored on the stack as integers are. If a type implements the copy trait, variables that use it do not move but rather are trivially copied, making them valid after assignment to another variable. Rust won't let us annotate a type with copy if the type or any of its parts has implemented the drop trait. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to that type, we get a compile time error. To learn about how to add the copy annotation to your type to implement the trait, see derivable traits in appendix C. So what types implement the copy trait? You can check the documentation for the given type to be sure, but as general, any group of simple scalar values can implement copy, and nothing that requires allocation or is some form of resource can implement copy. Here are some types that implement copy: all integers such as u32, boolean types, floating point types, char types, and tuples. uh, Tuples, for example, only the integer ones, okay, but integer and string does not. Ownership of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy just as assignment does. Listing 4-3 has an example with some annotation showing when where variables go into and out of scope. File name, let s equal to string colon, takes ownership. Okay, here we have defined as function, then s should be destroyed after this. Let make mix copy, okay, x. Here x goes out of scope, then s, but because s value is odd moves, nothing special happens. S value there and so is no longer valid here. Okay, if we try to use after calling the take ownership, Rust would throw a compile time error. Obviously, the static checks protect us from mistakes. Try adding code to main that uses s and x to see whether you can use them and where the ownership rules prevents you from doing so. Return values and scope. Returning value can also transfer ownership. Listing 4-4 shows an example of a function that returns some value with similar annotation as those in listing 4-3. Let s1 equal to gives ownership. Okay, then okay, s2, I'm returning a string. Okay, then I have s1, I have s2, takes and give back s2. Okay, takes s2, then I think s2 would be invalid over here, right? So here s3 got out and is dropped, s2 was moved, so nothing happens, and s1 goes out of. So yeah, correct. The ownership of a variable follows same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using a tuple. Okay, this is an example. but this is too much of a ceremony and lot of work for a concept that should be common. Luckily for us, Rust has a feature for using value without transferring ownership called references. Oh yeah, brilliant. So we will check references in the next video. Thank you for watching. Bye.